Hi everybody, these are the notes for 3.7 Intro to Related Rates. We're going to go ahead and start with a little reminder of what we've been doing this whole time. If you remember way back when, we started with this definition of a derivative, which is in your notes here. It's f prime of x equals the limit as h goes to 0 of f of x plus h minus f of x all over h. And basically what this was doing is it was taking this secant line that we had, right? We're finding the slope of a secant line, which is the average rate of change, and we're making these 2 points on the secant line get closer to each other, right? So we'd make this blue dot approach this yellow dot, and as we did this is the limit as h goes to 0, where h is the distance between those 2 points. As h goes to 0, we'd notice that these 2 points get really close together, right? Even if we zoom in, we can make these points even closer, and if you get close enough, you can see that orange tangent line is basically right on top of our function, and our function looks pretty much linear now, right? If you zoom in close enough, our function looks like a line, and this tangent line has the same slope as our function at that point, right? You can see that orange line, if you zoom in close enough, is pretty much right on top of our function line, right? So the slope of that tangent line is the same as the slope of our function at that point. And that's what we're doing with the derivative, is finding the slope of that function. All right, so let's go over here to our notes, and let's remember that this whole time we've been finding slope, right? So let's just review some things about slope, right? Slope is rise over run. So let's just go to this secant line example. I had rise, and here's my run. But another way that we've learned about, like that hopefully you've seen before, is instead of rise over run, some people call it change in y over change in x, right? So let's just write some things about slope. Is rise over run. Some people in the past have used this delta y over delta x, which is that little triangle. And then at some point, and this is actually what the notation that was used when they were creating calculus, but at some point, it became difficult to write the triangle delta x, delta y over delta x. And so somebody just decided to, instead of doing the triangle, because it's hard to put into computers and stuff, but they could put in a d, so they used the first letter of delta, which is dy, and then dx, which just means the change in y divided by the change in x. And that is what we're finding, especially if we have that tangent line, like in this picture, right? Even though it's not obvious, but I can, if I know the slope of that tangent line, then I know the slope of my function at the point of tangency, right? And so we're finding dy dx, which is why you've seen all these different notations. We've seen f prime of x, but when we've seen y prime, but even like a better notation, if you want to think about it conceptually, is this dy dx. And then what we're learning today is that, well, you don't have to have only y's and x's, right? What if I had a graph? Let's just do a small little graph over here. What if I had a graph that was in terms of t and h, and I wanted to know the slope of something on that graph, right? So let's say I had like a, some sort of parabola or something, and I wanted to know the slope between 2 points. Then what would I be finding, right? What would the slope be? Well, this would be dh, right? The change in h, and then this little piece would be dt, and so the slope would be dh dt, right? It's the same idea. It's still a slope, it's still a rate of change, but then it's now in terms of h and t, right? Because those are the variables that I used in my on my axes. Okay, so continuing along those lines, we've been seeing this notation a lot, which is dx of something. And remember what this means. This means take the derivative, with respect to x. also known as find the rate of change with respect to x, right? WRT, with respect to x. And if we do some little problems here, if I say find the rate of change of x to x, you can just treat this basically like a multiplication problem, right? This is going to equal dx times x, which is dx, which simplifies to, well, dx over dx is 1, right? But then the problems we're actually learning are like find the derivative of y. You can basically just think about this as multiplication, right? D over dx times y. If you want to think about it as y over 1, then it's d times y over dx times 1, which is just dx. All right, and I could do this with any variable, right? I could take d dx of z or f or whatever, and I just get dz df, right? And so what we're going to get into a little bit later today is, well, we're going to start taking the derivative with respect to time. So it's going to be d dt, right? What's going to happen as time goes on? What's the rate of change as time progresses of x? Well, this, and now in this case, is going to be d times x, which is dx dt, which is this rate of change of x with respect to t. But notice how that's not going to cancel out. So if I'm taking the derivative with respect to t, then that derivative of x is not just 1, but it's dx dt. All right, and continuing, if I could do the same thing with what's the derivative of y with respect to t. Well, it's going to be d times y, which is dy over dt. The change in y over the change in t. Okay, and continuing on some of these, let's just do a few more here. If I take the derivative, let's just do a quick reminder here of like this one. If I take the derivative of x squared plus 3 cubed, we just want to remind ourselves how we did this, right? What we did is we'd kind of cover up the inside and say, oh, what's the derivative of finger to the third power? And we'd say, oh, well, it's 3 times, the inside stays the same, subtract 1 there, and then multiply by the derivative of the inside, right? So basically what was happening is this whole thing was kind of like our u, and then we multiplied by u prime on the outside. Okay, so let's look at another type of these problems. So what if I'm take the derivative with respect to t of y cubed? Well, that's going to be d dt on this y cubed thing, which is going to give me 3y squared times, now the d times dy dt. That's the derivative of y with respect to t. Right, and so just like we learned before with like implicit, is if this variable does not match this variable, there's going to be this tail on the outside. All right, so let's look at some examples that will maybe help us understand this notation a little bit better. Okay, so we're given that this function x is 2, this should say y, x is 2y cubed plus 2. And I want to find dy of, so we want to find dy of 3x to the 4th minus 5 cosine y. Right, again, you can just think about this as kind of like multiplication. So this d dy is going to distribute to everything inside this parentheses. Oops, this is a y. So over here, I need to take what's the derivative with respect to y of 3x to the 4th. Well, this is going to be power rule. Bring down the 4, 12x to the 3rd. And then over here, I have the derivative of the inside, which is the derivative d times x over dy. So because I'm taking the derivative of y, or with respect to y, of x, I get this dx dy. Okay, and then we have minus, we're taking the derivative over here. dy of 5 cosine y is going to be 5, negative 5, because the derivative of sine, or cosine is negative sine, y, times the derivative of the inside, which is dy, right? The derivative of this, if you remember the rule that we learned for cosine, it's derivative of cosine u goes to negative sine u times u prime. Well, this dy is that u prime in this case. But notice how that's just going to go away. dy is 1. So really we're going to be left with positive 5 sine y here. All right, and then notice over here we have dx dy, right? That's the derivative of x with respect to y, and here I have x, and over here I have y's and stuff, right? So I want like one variable, which in the beginning they gave me x is 2y cubed plus 2. So we're going to go ahead and just take that, and we're going to plug that in. Everywhere I see an x, I'm going to replace it with what x is, which is 2y cubed plus 2. So it's going to be 2 times 2y cubed plus 2 times dx, right? We're replacing x with 2y cubed plus 2. Right? And so now I'm taking d dy on this outside piece, d dy of 2x cubed, 2y cubed plus 2, and that's going to give us 12, sorry, this should be 3 up there, right? 12 times 2y cubed plus 2 cubed times the derivative of 2y cubed plus 2, which is 6y squared. And then this sine y thing keeps following us. Oh, and there should be like a dy after the 6y squared, but we don't need to take that, right? And so I'm left with this, which another way I could have done this is I could have, in the beginning, just directly substituted this in there and then taken the derivative, which, may have been easier or harder, but the idea is that you're seeing that this dx dy is, we're doing that because x is a function of y, and so we can, kind of take the derivative first, but we have to account for that chain rule thing that goes on there. Okay, let's look at another example. When you fix these variables, we got z equals 3t squared plus 1, and then over here we want to take the derivative with respect to t. I take the derivative with respect to t of z to the fourth plus 2 tangent t. All right. There's two different ways I could do this, right? The first way, I could just go ahead and substitute, right? So I could go ahead and just take this z and plug it in here, and I'd say, well, z is 3t plus 1. So I'm going to write 3t squared plus 1 to the fourth power plus 2 tangent t. And now everything's in terms of t, and I can just take the derivative, and I'll get derivative of this is going to be 4, 3, 2t plus 1 to the third times the derivative of the inside, which is 6t, plus the derivative of tangent is secant squared t, and then remember technically it's like dt, which is just 1. And then you could clean this up, 24t times 3t squared plus 1 to the third plus 2 secant squared t, dt is 1, and I would get that, right? So I could do it that way. Another way I could do it is take the derivative of this first, right? So I'm going to put a line there, and let's take the derivative of this first. If I take the derivative of that first, then I get 4z to the third times the derivative of the inside is the derivative of z with respect to t plus 2 secant squared t. And then now that I have the derivative, I can plug in, and I get 3t squared plus 1 to the third, right? I'm replacing z with z. And then I have dz dt there, right? So I'm replacing my z with z, which is 3t squared plus 1 still. And then this guy is just following us along as we go. All right, so now If I'm doing it this way, I have, well, what's the derivative of this with respect to t, right? And so that would just be, you know, okay, for this whole thing's the same. I'm only taking the derivative of this piece right here, right? The derivative with respect to t of this is going to be 6t. And so you can see how in both cases we got the same answer. Well, we will get it if we multiply that 6 times that 4. We'll have this exact same thing. So there's kind of several ways you can think about it. But hopefully this is helping you understand like this notation a little bit better.